The first speaker of this session is Stefan Wiens, and the reason he's here this year is because he was here last year and he found it so good and inspiring. So this year he's going to give a talk.
Yes, thank you very much. I was really my background is in experimental psychology, and my training was for most people like not really about basic. It was really about frequentist statistics. So I was really naive until like about a year and a half ago. I started looking into it, and then I came here, was totally inspired to say I have to do something about this. So I was working on a paper, and you can see that it's drifting over, really trying to go from the traditional to more Bayesian approach. And if you want to download this stuff, it's if you Google my name, Stefan Wiens, SU, and then it's the second one. I think it should list this one at Stockholm University. If you go there, then you're based at Lund, you can get a link to the Prezi presentation or the PDF or a link to the publication. Yes. Okay. Should be working now, but it doesn't accept this. Maybe it doesn't. I'll use that one. Okay. In psychology, there's been a movement towards new statistics, and Jeff Cumming is one of the main contributor into the discussion. And the new statistics, they say, you all go away from the p-value stuff, go towards effect size, focus on effect size, and report confidence intervals, 95% confidence intervals. And my colleague and I, Mats Nilsson, we asked, what about factorial designs? That's really very standard in psychology. You want to look at mean differences, and you have factorial designs. So something like this, right? You have 3 groups, a weighting group, a cognitive behavioral therapy group, and a meditation group. And then you have time as the other variable, so 4 levels. For example, 2 weeks before, and so on. So this would then be a 3x4 ANOVA or factorial design, and you would typically analyze this as an ANOVA, and therapy by time. So if you use the standard approach that we were trained in and that we were still told to teach to other people, you would look at 3 effects: a main effect of therapy, a main effect of time, and the interaction between therapy and time. Right, so the main effect of therapy would have 2 degrees of freedom. It just says, are there any differences between the 3 groups? And the main effect of time would be, are there any differences between the 4 levels of time? And then the interaction would be like a mess, basically. But would say these differences between the time, do they differ for the groups? So I think you already heard from what I said, it's kind of not very specific, right, these tests. It just says there's something going on. And then what about effect size? Yeah, we were told yes, to say report effect size, and then what's the standard would be like partial eta squared or eta squared. And I'm not a statistician, but I read some articles about it, but I still don't really understand. Like, it's not intuitive. I think I understand it, how it's defined, but to me it's not very informative. So we were thinking, what can you do about this? Like if you have these new statistics in mind, effect size and confidence interval. So we said, what is effect size? And it's basically the size of anything. You can say like the distance to the moon would be an effect, and or how much chocolate is in a cookie. I'm actually not sure, I made this up, 23 grams. Yeah? And then you also think about effect size really concretely, right? Like I had this actually for a while. I was so annoyed by this significance testing that when you ask a physicist, how long is it from here to Stockholm? A physicist would tell you it's like 600 kilometers, whereas a psychologist would tell you it's significantly longer than to Malmö. Yeah, it's not very informative. So you should think in terms of an effect size if it's practical or clinically important. And then also standardization, there's an issue in psychology, what we experience. Many people, they want to move to standardization because it's like cleaner. like to use Cohen's D or correlations. But I really like this quote by Tukey. Are we so disinterested in our variables that we do not care about their units? Yeah? Isn't it much nicer to know, like in kilometers, it's meaningful, give me the distance, or give me how much gram chocolate there is. Yeah, so avoid standardization. All right. And as an answer, what we found was contrast analysis. And this has been around for a long time. So I'm not saying like, oh, we invented this or something. It's really like in many textbooks, they mention it. But my own experience was when I read it, I was like, that sounds interesting, but they didn't really explain it enough. So by Rosenthal, 1999, they went in more detail. But we thought maybe it's not somebody that everybody knows. So we dug it out again. So the simplest contrast analysis would be a t-test. Yeah, so if you have a minion and then you train, it works out. So you before it starts the workout and then after training. And then if you do a t-test, you say like 8 kilograms. Actually, don't know what they weigh. I didn't Google this. Yeah, so you get the point, right? 8 kilograms and goes up to 13 kilograms. And how would you analyze it? You would say, I'll take the 13 minus the 8. Right? That's the increase, the weight increase. So you would find 5 kilograms. So you can think of this as saying the after you weigh it by +1, that mean, and the other one, the before, you weigh it by -1. Okay? So then this is already a contrast. You're contrasting two means with each other. Now what about if you look at long-term effects? Yeah, so you have before, after, and then 12 weeks later. After the training. Yeah? So you have 8 kilograms, 13, 15 kilograms. And now you just want to still compare after with before. Right? You would say, like, how can I do this in a t-test? Yes, it's the same thing as a t-test. You can still apply a t-test. And but what you then have to do, you just weigh them. You combine these two means. Right? The after means. The after 6 weeks and after 12 weeks, you combine them. And you combine them like intuitively. You say, take the average of these. And then see the average of these compared with the one before. So this is then a contrast analysis. It's basically a mean difference between sets of means. Right? Combining the after means, the two after means, combining it with the before. Comparing it with the before. And then you would get, here if you figured out, it's 6 kilograms. Yeah, after minus before. So that's a contrast score, and that's really the effect size. It's an unstandardized effect size, right? The mean difference. So that's what you can work with. So we thought this is nice to use this contrast analysis approach. And it's actually ANOVA and contrast analysis, they're very similar. So it's not that now you're shifting to something completely different. Because any ANOVA is actually a combination of contrast analysis. So if you have a 2x2 design and you are interested in the effects of here antivus and alcohol, then if you say I'm interested in the effect of antivus, you would say what's the column? Take the average of the first column versus the average of the other column. Yes, so you would weigh the first in the left column. You would weigh each cell by +0.5, and the other one by -0.5 to the right. If you want the row effect, you would do something similar, right? Get it? And interaction, you would look at the diagonals. So this is actually the standard set to run an ANOVA. The two main effects in the interaction in the 2x2. But what is nice with the contrast analysis, you can make it as complicated as you want. So if you're aware of this effect of antivus by itself should make you nauseous. And alcohol by itself in moderate quantities should make you nauseous, right? So it's only if you combine them, you should get this effect. So you could say that's maybe a synergistic effect. So just consuming antivus or alcohol by themselves won't do anything. It's only in combination. So then you could use this kind of contrast set that you say it's this cell versus the combination of all the other cells. That's where the effect is. Make sense? All right, and then you can go on and make it as complicated as you want. Yeah, so if we go back to this 3x4, you could extract a specific effect to say, okay, I'm interested in the effect of the treatment, the cognitive behavioral therapy versus the meditation group. So you would start off like this, saying after, for the CBT groups, after versus before. And then you would say, this difference, does that differ from the difference for the meditation group? Okay, I think it's obvious, right? That you just say this difference minus the other difference. If I talk about difference between differences and differences, it gets too complicated, right? I think you get the point. So this difference for the CBT group, does that differ from the difference in the other group? And what would you do with the weighting group? You would just weight them as 0. Yeah, you're not interested in them for this contrast. You can also do something like, if you're then interested in, I'm interested in the effect of the treatment compared to the weighting, right? So you would start with something similar for the CBT group. You would say after versus before, but then you want to combine the CBT with the meditation group. So, right, this combines all of the after cells and contrasts us with the before cells. And then you say, this difference that I get in the clinical group, does that differ from the difference in the weighting group? So you could do this. Make sense? Right? All right. So you can make it complicated. So, and then we thought, okay, now we have this, we can use this contrast analysis to have a factorial design and extract like meaningful effect sizes, right? Because then if you figure it out, weigh the means, you get a contrast score that's really the mean difference in the unstandardized, in the raw unit. Yeah, so if you say this is happiness, this was the dependent variable, you would say how much did happiness improve in the clinical therapy groups versus the weighting group. All right, so that was the first part, but then what about to say, is there an effect, right? The significance testing. But then if you look at significance testing, I think, yes, I don't want to preach to the choir here, but in our department it's still like, what do you mean significance testing? It's been used for so long, so it must be wonderful. So the significance testing is kind of blind. It only looks at the null hypothesis. Yeah, so it says here, if you say a boxing match, the judge looks at the null hypothesis. The null hypothesis is down, so I say the other one is the winner. Even if the alternative hypothesis is also down. Right? It doesn't care. It's really hypothesis myopia. Right? It's really blind to saying like what's actually going on. I'm just declaring somebody a winner, even though I don't know what the winner is, or that the winner is also not good. All right, so then, so the p-value isn't so great. So now, what about the next step? And in this new statistics, they advocate the confidence intervals. So, and we were thinking, is this maybe like for many people, it's like p-value, and the confidence interval is something completely different. But it's actually, I take this kind of shortcut. If you think of a t-test, right, you would do this for means. You would do a t-test and say, I sent it on 0, and then I have a non-rejection region, right? The 95% non-rejection region. And then if I have my observed mean, it has to be outside of this region, and then I say it's significant. And the confidence interval, you can think of it, center it, this non-rejection region on your observed mean. That's what you would do. I know, it's like for statisticians, they're like, and Cummings said, no, it's not correct. But I think it helps me and helped other people, I hope. So I'm taking a shortcut. Yeah, so it's basically, you are centering they call non-rejection area on the observed mean. All right, and then also with the confidence, there's always this discussion, what is confidence? Oops. Nobody wants to know this. How do I have to do this, I think. Right, that the confidence is not about an individual confidence interval, it's about the procedure. Right, so this is a nice illustration with the ASCII. That's Jeff Cumming has this in Excel. Nice software to illustrate this. So this is simulated data, and you get all these kind of confidence intervals, and most of them are green. So they capture the true population value that's at 50, but then sometimes you get a red one. So that one doesn't capture. So then this 95% refers to, if you did this over and over again, 95% of the time you would capture the true parameter, and 5% of the time you wouldn't. That's what the 95% stand for, not for an individual confidence interval. Okay. But then if you've read this paper, and I'm still chewing on it like again and again, because it's very dense and there's a lot of arguments in it, but they trash confidence intervals in a nice, no, not in a way nice way. I mean, I kill it. To me, it sounds like they really kill it. That they say it's like it has been really misinterpreted. And I asked the statistician, he said like, oh, we already know this, have known this for a long time, but in psychology this is hasn't really dribbled down completely. So they have this really nice paper, Fallacy of Placing Confidence in Confidence Interval, that it's actually, the confidence interval is also interpreted to mean like if you have a narrow interval, it means you have more precision than a wide interval. And they show and they argue and show that it's wrong. And yeah. So you can interpret confidence intervals that way. And I have to say then our paper is wrong, because we went with it, just assumed this is how everybody talks about, but now I know it's wrong. So you shouldn't use this confidence interval in terms of precision and likelihood. You have to use credible intervals. But as an excuse a little bit is that if you use t-tests and go with all the assumptions, then and use an uninformed prior, the confidence intervals and the credible intervals are numerically identical. Yeah? So it doesn't excuse this, but if you just have like a standard software and say like, oh no, I don't know how to use more Bayesian approaches, so can I just use the standard softwares? Yes, you can, right? Because it spits out the confidence intervals, but you can interpret them as credible intervals. All right, so so we actually have some R scripts that you can download. They're actually a supplement to the paper, but I checked on their website, they got rid of the supplement. So at the journal, it's already gone. So I have to email them, like why they don't want to keep supplements. But you can download this stuff, yeah, in the link. And so it's really just a basic R script, nothing fancy, where you can say, oh, I have this ANOVA, and then you set up the contrasts, yeah, the weights, and then it gives you the contrast weights and now the CIs, and yeah, then you say these are the credible intervals. And then it also gives you this nice table. I think it's kind of neat. Yeah, the table with the weights, and you can standardize the weights if you want to, or you can, and the credible intervals. And also in psychology, it's still please report everything, even p-values and so on. So you can do this. Right, and then if you know credible intervals, they're more informative, right? If you look at the left one, you would then say, oh, the A is less precise than B, even though they have the same p-values, right? It's more precise. And C and D both say there is an effect, but C is less precise, and so on. Yeah, you can look at this. And but then a confidence interval is really about like parameter estimation. Credible intervals about parameter estimation. But then in psychology, there's still a lot of hypothesis testing. Is there an effect or not? Yeah, and many people now advocate to use Bayes factor for that. Yeah, so we also have this example, like what about if you wanted to do a Bayes factor? So here somebody could say, all right, if these are the observed means, you have like 16 for this combined cell and about 4 for the other ones. That looks like a synergistic effect, right? It's really if you combine both, then you get an effect. So you could use these weights. Yes, in this one cell in the left corner, the upper left corner versus the other ones. But then somebody can say, but maybe look at this. If you just have antabus by itself or just alcohol by itself, then you already have a little bit of an effect, right? It's small, but maybe there's an effect. So what you can do is then to say like, oh, does this support the null hypothesis that there's no effect, or is there an effect? And that's where the base factor comes in. So, and one nice software is Jazz. I mean, like if you know R and so on, or Python, then it's like, yes, you can just do that. But then if you're still struggling with SPSS, trying to get rid of that, then this is really helpful. But then with Jazz, we use default priors. Yeah, but then you get really nice pictures where it illustrates the base factor, like in a pie chart, then, and then also with the posterior distribution. And another one that I think I like a lot is, because it's kind of simple, it's like this online calculator that Salter and DNS has provides. And then you can also have R scripts for it. Where you say it's not just the default, but really say what makes sense. A uniform, half normal, or normal distribution as a prior. All right, to summarize this, basically you have factorial designs. If you start with it, it gets really kind of messy, right? You have a 3x4x5 design or something, and it's like, yes, we find some interaction here. And then what does it mean? It's like, do you want this where it's just everything thrown in? Why not use? Why not ask specific questions? So do a contrast analysis, because then it's more specific, informative, and you are actually, the difference that you get out is the effect size that you can interpret. And then instead of confidence intervals, go to credible intervals. And if you really want to do hypothesis testing, go away from the p-value stuff and do base factor. All right. All right. Thank you very much.